All right, there we go. Okay, welcome back, folks. I hope you guys had a good break. You were able to relax a little bit or catch up on the quarter, and are excited to get back into the last stretch. We have 5 more weeks, so we're halfway through. Hopefully that goes smoothly. A few announcements before we get to the actual meat of today's session. The homework one for semaphores is going to be due tonight. If you haven't started it yet, please start it. There is one problem that we have used, then reused, then reused in there. So you're just going to be able to get that from your activity quite easily. We have an advanced semaphores homework that's going to be due on Thursday. I highly recommend, even if you don't want to submit advanced assignments, that you actually go ahead and do this problem, because it's going to be really helpful to give you more practice for the second exam later. We have an activity due tomorrow before class, so that's today's activity going to be due tomorrow. Probably we'll finish it off in class during this time. Recall that milestone 2 is due next Monday, so keep that in mind as well. Start early and ask questions if you need to. We're going to have a work day on Friday, so you could use that time as well. Second set of announcements. Exam 2 is going to be on Friday of next week. So not this Friday, next Friday, about 10 days from now. So what we're going to cover are basically everything after exam 1. So threads, semaphores, mutexes, condition variables, up until tomorrow's lecture. Okay? So there will be one pthread question, and there are going to be 3 other questions on semaphores, mutexes, condition variables, and so on. Okay, so make sure you refresh that. We had 3 homeworks on semaphores, so you should be dreaming about them now by now, right? I'm still deciding between a night exam and an online exam like we did last time. Still on the verge of that, so I'll let you know once I figure that out. Probably within this week, I'll let you know how things are going to go. But it's definitely going to be on next slide. Yeah. Inodes and all of that? No. Yeah, just threads, semaphores, and everything on those until today.
Until today or tomorrow?
Tomorrow, sorry. Yeah. Tomorrow is going to be more semaphores, so just going to keep going at them. Questions?
Is that week 6 or week 7?
This is week 6, so it's going to be Friday of week 7.
Okay.
Yeah. All right, so today we're going to be talking about a new semaphores problem. It's called the readers and writers problem. We're going to see different approaches to solve this problem. They're going to see the shortcomings of each, and hopefully by the end of the session you'll have already completed your activity, so you wouldn't have to worry about it for tomorrow. This is one of the solutions this is one of the cases where a unique or a single semaphore is going to prove not to be enough for us achieving that. All right, so we're going to see that as we go forward. A quick recap, though, I'm sure you've been tired of semaphores, so I'm just going to add to that and just remind you real quickly what they do. A semaphore is an object that has an integer value. If you wait for a semaphore, you decrement the value, and you block or you sleep if the value is less than 0. If you post to a semaphore, you increment the value, and if there is anyone sleeping, then you're going to wake them up. Okay? Yeah.
What do you block if the value is less than 0? Is that counting before or after the decrement?
After decrementing. So you first decrement. So if it's 0, it becomes -1, right, and then you block. Right. There is an implementation outside of pthreads, the standard, where it does the opposite. Right. Yeah, it depends on, then you have to adjust your post accordingly. Right? Okay. a quick recap about a mutex. A mutex is very similar to a binary semaphore that can only be in two states, locked or unlocked, 0 or 1, okay, or 1 or 0. You either have or own the lock, or you must wait for the lock, and those are the functions that we discussed and we saw last week when we talked about the mutexes. Okay, so let's go ahead and jump into our problem. So the readers and writers problem is defined as follows. We have a shared memory region, okay, and we have two types of threads. Oops. We have readers or reader threads, and we have writer threads. And we have at least one writer and at least one reader. Usually you have many readers and many writers. So as their names suggest, all the readers are going to do are just going to read the value. They're not going to change it. They're just going to read the value, right? The writers, on the other hand, they're going to write and update the value or to the memory region. It might be just a simple integer, might be something else. The only trick is that only the writers are allowed to update the value. The readers are just allowed to read the value. Yeah.
Do the writers share the same memory region?
Yeah, they share the same memory area. Yeah. So this part is shared among multiple readers and multiple writers at this. Okay. So first question is the following. If I hide this part, so I'm just looking at this picture this way. Let's assume writers don't exist. Do we have race conditions and should we be worried about them? Yeah.
I was going to say no, because anyone can grab it and look at it at the same time as long as they're not changing it.
Yeah, exactly. So recall the definition of a critical region and a race condition, that there must be an update happening to the shared variable or to the shared memory area. If there's no update happening, then it's not really a race condition. It's not really a critical section anymore. So between the readers themselves, there is no race condition. We can have as many readers as we want. They can all read at the same time. It doesn't really matter, right? Because the value is not changing. The problem comes in when we include the writers in this process. So can you think about what are the race conditions in this case? So what are the possible race conditions in this setup? Yeah.
Writers could write at the same time, we can see that it's one value, so it's did it correctly.
Yep. So first race condition is multiple writers update the data at the same time. Okay. So is there another one? Could there be another case where we have a race condition? Yeah.
Readers kind of read at the same time.
Yeah, exactly. If I have at least one reader reading at the same time as at least one writer. Okay, so it's obvious that we have two race conditions, and we must ensure that our concurrency mechanisms, whatever we want to do to solve this problem, takes care of both these race conditions. So out of the blue, like if I just throw this problem at you, what's the first thought that comes to your mind? Yeah, Avi.
Map the mutex that's the memory region if you ever want to modify anything inside the mutex.
Yeah. So if I just throw this problem at you, your first reaction is probably going to be just lock this entire region, right? Let's say I use a semaphore, so I do semaphore wait in here, semaphore post in here. Okay? So that seems to solve the problem. It covers this case, and it also covers this case. So let's actually implement this and see what happens. So you don't have to code along this part because we're just going to change it a little bit later on. But we're just going to try to see what happens and see if we can pinpoint any problems that arise. All right. So this is our code. The reader only is going to read the data and print it out to the command line. The writer, on the other hand, is going to change the data, increment a shared variable called data by 1. Okay, and we have, in this case, 0 and 1, 2 writers and 5 readers, right? I'm going to use just 3 writers to make things a little bit more interesting, so I'm just going to increment this to 2. Okay, so we have 3 writers, 5 readers. So before we said that our initial approach is that we're going to lock the entire critical section. So to do that, we can use a semaphore or we can use a mutex. I'm just going to use a mutex so we can get a flavor of on both of them. Okay, so I'm going to call it lock. So the critical section for the reader is when they're going to print F. So what I'm going to do is going to have to pthread mutex lock in here. And once I exit the critical section, I have to unlock the mutex. Okay? The same thing is going to happen on the writer side. Before my critical section, I'm going to lock the mutex. And then after my critical section, I will unlock the mutex. Right, and last thing I want to do is basically just initialize the mutex. Oops, 0 and okay. Since this program never ends, there's no point in destroying the mutex because there's no exit point in this code. But generally, if you initialize a mutex, if your program exits, then you must destroy the mutex before you leave. Otherwise, you're just leaking. Okay. All right. So let's go ahead and compile this. And this is section 4. Okay. So it seems to be doing something, working well. Can you notice anything that kind of looks fishy or looks annoying or beats the purpose of using threads in general? Yeah.
Like if the readers themselves are blocking the other readers, so if one reader is reading, all the others can't read as well.
Yeah, exactly. So as you can see, things are happening sequentially. I'm only allowing either one writer or one reader in my critical section. But as we said initially, if we just look at the second half or the first half of the picture, if the writers are not allowed to go in, then the readers can actually go in and do all of their other things as well. Right? So we're not making use of this fact. We're not making use of the fact that if the writer is blocked, then multiple readers can go in. Right? So we need to solve this problem. So next, so our initial solution, solution 1, was that use mutex to log critical section. And the problem with that was that only one reader can read at a time. Okay, so in order for us to solve this problem, I'm going to give you an analogy that can help you think about this problem, and then hopefully you can get to the solution on your own in the next 10 minutes. So this is your dorm room. And you're just throwing a party and asking everyone to come in, right? So you have students coming in to the dorm room. At the same time, you also have cleaning staff that want to come into the room and clean and update the room. What you want to do is you want to allow, if there's cleaning happening, then no students can party, right? Because the janitor is inside and clean. But if the janitor is not cleaning, then you don't want students to come in one by one and then leave, right? That's not a party anymore. It's just people walking into a room and then exiting one after the other, right? That's not really what we want to happen. If the janitor is not cleaning, then as many people as we want can go into the room and have a party. Okay? So you might have cases where you have people inside and maybe some music playing or something along those lines. All right? So how would you solve this problem? I'm going to give you the next 10-ish minutes to start thinking about this problem. You can bring up your activity. It's going to be under 21 semaphores 2, and you can start writing your solution if you'd like. Please don't look at the solution yet. It's sitting there, but start thinking about it and see if you can get to a point where you can solve this. And as a hint, you might find it helpful to keep track of students that are in the room.
Are we supposed to wait because are we assuming if the cleaning staff wants to come in, does it kick everyone else out?
No, they don't have the power to kick anyone.
Okay.
They have to wait until the room is empty, right? Yeah, so they're basically all done. But I'm going to update. Whenever they like update, we need it. So that's you're kind of looking for the last 10 minutes. So we're going to come back to that. Okay, any thoughts or ideas about how we would approach solving this problem, which is allowing multiple readers to go in at the same time if there's no writers coming in? Yeah.
Because we did this, we've been doing it for some time, but we have a way of keeping track of how many students are, like, readers are reading.
Yeah.
And then the while it's less, while it's waiting, we just wait for the condition to.
Yeah, yeah. So that is great, actually. One thing we can do is we can set up a condition variable that says, you know, I know how many students are in the room. So the first, what I'm going to do is that the writer is going to wait on that condition variable. And then only when the number of readers becomes 0, then I'm going to signal to this condition. All right, that solves the problem, which is pretty good, right? There is a slight tricks in that, so I leave you to think about those. And we're just going to focus here on solving this problem using just semaphores and mutexes. So here's an idea. If I am the first person to go into the party, what should I tell the janitor? Yeah.
Lock out the cleaning staff.
Yeah, exactly. So if I am the first person to go into the party, then I can place a sign on the door to tell the cleaning staff that there's a party going on, please don't come in, right? And assume everyone's going to honor each other's word. Like, we're not lying, and the janitors are going to wait if they see that, right? So they're not going to kick anyone. So who's going to remove that sign? Yeah, the last person to exit the party, right? So the first person to enter the party is going to post a sign that says readers are in or students are partying. And then the last person who leaves is going to take down that sign and tell the cleaning staff that they can actually go back. So we see now that we're using another form of synchronization. So we're going to introduce another semaphore. So let's call that semaphore. Let's call it party, actually. Right? So we introduced a new semaphore. What are the readers are going to do? And we're actually tracking the number of students. And I think we had that mutex called block. Okay, so what we're going to do is that the reader is going to go into the room. So they're first going to lock So I'm just going to use a shorthand here, lock and lock. So lock the mutex. They're going to increment the number of students in the room. So we'll leave what they're going to do else after that. And then they're going to unlock the lock. They're going to read, or basically party, which is pretty much a lame party if all you're doing is reading, but that's what happens in here. After they leave, they're going to get that lock again, and they're going to decrement the number of students, and they're going to unlock the lock. So as you can see in here, we changed the semantics of the mutex. The mutex initially was protecting the critical section, this critical section, right? But now the mutex is actually protecting this critical section, which is changes to the number of students in the room. Okay. So what else is going to do? What else are we going to do in the reader? If I am the first one in, so if students is equal to 1, then I'm going to hang the sign, which is basically going to say I'm going to get the party semaphore. So sem wait and party. So I'm going to put the sign on and say there is a party going on. Janitors, please don't come in. And before I leave, if I am the last one in, so the last one leaving, last one out, so if we are at 0, then I'm going to sem post to the party. So basically saying that the party is over. If anyone was waiting for the party to be over, then they can just go in. So given that, what do you think the writers are going to do? What are they going to wait for? What are they going to post to? And what are they going to do? Yeah. Okay. So which lock are you going to acquire? Is it lock or party? We have two of them. Okay. So if I try to do this, okay, if the writer tries to wait on the party lock, if there are students in the room, what's the value of the party lock or the party semaphore? So in a sense, what we're asking is there a sign on the door when the students are partying? Yes, because the first one put it in. So here's where the first one put the sign. So someone has put the sign, which means they put the value of the party semaphore is now -1, right? Or basically 0 in a sense. So when the writer tries to come in, they're going to see that the value of party is 0, meaning that there is a party sign placed on the door. So they will just wait eventually, or wait until that post happens. When is the post going to happen? When the last student leaves the door. So this blocks when students are greater than or equal to 1, and it unblocks when students is equal to 0. And then they can write, which is equivalent to clean. And then they're just going to post on party. Okay? Questions? So let's go ahead and implement this as well, and see if there are any problems with it once we do the implementation. So I'm going to add a semaphore called party.
So when you're done, you post back the party?
Yes.
So that way the student.
Yeah. So when you post, when the janitor, all right, let's go back. When the writer has acquired party, party becomes 0, right? So when the first student tries to come in and wait, they're gonna get blocked. So in a sense, what the janitor does is anytime they go in to clean, they're gonna take the sign with them. They're gonna prevent anyone from hanging the sign. So if there's a student that wants to come in, they're not gonna be able to hang the sign because the janitor has it. Okay, so and we need students. We start from 0. So this is going to be readers in this case, so let's just use readers. So let's fix the writer first. We said we're going to do some wait on party and some post to party. That's all the changes we need to do to the part to the writers. So what we're going to do in the mutex in the section that the readers are going to be doing, we're first going to increment readers, and we have to check if we are the first one in, and we're going to wait on party, and then unlock. Then after we're done, readers minus minus, and if readers okay. So in a sense, we are implementing a condition variable, right? When this happens, this is when we signal to the condition variable. When this happens, we are waiting for a condition variable. So in a sense, we're kind of simulating a condition variable in this case. Okay? So, and we need to initialize our semaphore. So let's go ahead and do that here. And we call it party 0 and initial value is 1. Okay. So let's go ahead and compile this and see if it works. So as you can see, when a writer starts, the writer finishes. No one else can be allowed to go into the critical section. The same thing happened here. Writer 2 also did another turn, so no one else was allowed in, neither another writer nor any reader. But when the readers started to come in, they came in all at once, right? Or not all at once, but like in a very close time to each other, right? They're allowed to come in all at once. Okay, so 2 questions I have for you. Why didn't I use a mutex for party? Can you think of a reason why I would prefer a semaphore over a mutex in this case? Yeah. Okay, so we can have multiple readers and multiple readers go in, but the value of the semaphore party is at most going to be 1, right? So here's a question for you to help you a little bit. Is the person who posts or who puts the sign on the door necessarily has to be the person who removes the sign from the door? No, right? So the first person in is not necessarily the last person out. They might leave the party early. So the person who hangs the sign on the door is not necessarily the one who is going to remove the sign from the door. Now, the problem with mutexes is that, by definition, whoever locks a mutex has to be the one who unlocks that mutex. No one can unlock a mutex on behalf of another thread. If you do that, the behavior is undefined. Sometimes it works, sometimes it doesn't. It depends on your compiler, it depends on which version you're running, what machine you're running, what operating system you're running. Okay? So it's a general rule. Whoever locks a mutex has to be the same thread that unlocks that mutex. Don't interleave locks and unlocks. You can interleave semaphore waits and semaphore posts, but you cannot interleave locks and unlocks on mutexes. Okay, second question. Let's run this and see if you can notice a problem. Keep it running a little more.
If you initialize, just make sure you're right. You initialize, put sim in it to 1.
Yes.
Okay.
Yeah. Let's reduce the number of writers so we can see it more clearly. And then we're going to reduce that to, let's just have one writer in there. So can you see a problem that's kind of happening now? We scroll back. We can't scroll back, but. Yeah.
The readers and just kind of keep reading and not let the writer.
Yes, exactly. So the way we have set things up for now, if there is, let's say, the person who threw the party is really, really, really popular. So they have everyone in the university joining in that party in the same room, right? So people are going to come in, maybe come out, but then new people are going to come in, new people are going to come in, new people are going to come in. And if there's a janitor waiting, then we're going to have a problem. The problem is we refer to the problem with solution 2. We refer to this problem as starvation, where a thread is waiting for some resource, but that resource is never being delivered to that thread, right? Which is the writer or the janitor is waiting on the door for the students to leave, but the students are never leaving. So do you suggest a solution to this problem? Can you suggest a solution for this problem? What can the janitor do to prevent this problem from running, or to prevent starvation in a sense? So one thing I will jump ahead and tell you, they cannot kick anyone out. Okay, so can they do something to make sure they don't starve? They don't wait for resources indefinitely for a long period of time. Yep.
Whenever they grab the lock, hold, and make everyone else drain in and out.
Yeah, something very similar to that. What they're going to do is the cleaning staff or the janitor is not going to allow new students in. So whenever the janitor comes in and they want to clean, they're going to lock the door from the outside. from the outside, no new students can come in because the door is locked and they don't have the key. The students that are inside are going to continue to party, but then eventually they're going to leave, right? So no newcomers to the party are allowed. The janitor is only going to wait for those who are inside to leave. So they're going to lock the door, and then they're going to prevent newcomers from coming into the party. So let's see what changes in the writer end. So we had lock, party, students, and now we're going to introduce a new semaphore. Let's call it door. Okay, so what the writer is going to do is it's going to wait on the door. Or actually, let's use a mutex because it's kind of more in line with the terminology we're using. Pthread, mutex, T, and door. So we're gonna lock the door and wait on party. And write then post to party and unlock the door. Okay, so what do you think the readers are going to do differently? So let's bring in their old piece of code. Oops. I suck at this. So let's look at this piece of code. What are the readers going to do differently? What are the newcomers going to try to do when they want to come into the party? Yes.
Unlock the door.
Yeah. So what they're going to try to do is they're going to get the handle of the door and try to move it. If it's unlocked, then they can go in and leave the handle. If they see that it's locked, then they're just going to have to wait along with the janitor until the janitor finishes everything up and locks the door. So what they're going to do is they're going to try to lock the door, or take the door lock and then directly unlock it. So if the door is unlocked, then they're simply going to twist the handle and go in. If the door is locked, then they're just going to have to wait here until the janitor unlocks the door. They can twist the handle after. Okay? And then the same code is going to apply here. So here's a general rule that you must always remember when you're dealing with multiple semaphores and multiple mutexes. The last semaphore or mutex you lock or you wait on is the first one that you post to or you unlock. The first semaphore or mutex you lock or wait on is the last one that you're going to unlock or post to. So always kind of treat them as curly braces. The last one you open is the first one you close. Last one you lock, first one you unlock, first one you lock, last one you unlock. It's generally a good idea to always do that because it can prevent deadlocks if there are any possibilities for deadlocks. Okay, so that's all you need to implement for the activity. You just need to add these 4 lines of code and you should be all done with that. Yeah.
The lock and unlock, is that going in the critical section?
So this is before the critical section. So basically, before I enter the room, I'm going to try to open the door, right? Yeah.
So if the reader doesn't have the lock, like if it's locked by the writer, they can hit the try lock, just nothing happens.
They're gonna wait, right?
Oh,
Yeah, so basically they're gonna try to open the handle, they're gonna see it's locked, and they're gonna have to. Yeah,
What happens if it locks, unlocks, and then right then it gets interrupted and goes to the writer or something?
yeah, so if it locks, unlocks, let's say here,
Right.
it goes into this, right?
Yeah.
Two things might happen, right? Either the writer is gonna already have acquired the party lock, and the if he, I should let me bring this code down there so you can see it more clearly. Okay. So if I acquire the lock door and I get thrown out here. Okay. So there's two possibilities. The writer is going to go in here, but they're not going to wait on the party yet. They get swapped out. When the reader goes back in, they're going to wait on party. And thus, next time the writer comes in, they're going to block here. Because this guy has already been acquired by the reader. The opposite can happen as well.
Sorry, go over the first one again.
Yes, so let's draw this out in a sense. So we're going to execute lock, unlock. Then writer is going to do lock on door, right? And they're going to do, let's say they do wait on party. Okay? So what's going to happen after that? So if this works, then this is the first one going into the room, right? So if, let's say they got swapped out back here now. So what's going to happen is that we're going to increment students plus plus. We're going to check if it's 1, because it is 1 going to be now. So we're going to wait on party. But here, we're going to block, because party belongs to the writer. And you can flip this the other way. You can say this happens. We jump back here.
Yeah, that would, I feel like that would cause the same problems problem you had with the start.
Yes, but this is much more unlikely
Okay,
to happen.
so it's not a perfect fix, it just fixes it.
Yeah, so it's not a perfect fix, but there's no way you're going to prevent this. If you have like 10 million readers and one writer, probably the writer is going to starve a little bit, but effectively, this is going to reduce the wait time for the writer.
Okay, thank you. You have time to answer one quick question.
Sure. Let me just